I am trying to get a handle on how to convert an equation from one set of units to another set of units. I'm fairly familiar with how to convert individual quantities, but I am, for instance, like 1 cubic yard equals 3 feet cubed, which is equal to 27 cubic feet. But what I want to do right now is go through a couple of examples where we take an equation that we know in two different forms. Let's change that to a theta there. And this is the equation for angular resolution of a telescope where theta is given in arcseconds, lambda is given in micrometers, and d is given in meters. Here is the same equation where theta is given in radians, lambda is given in meters, and the diameter is given in meters. Now this equation right here is called Kepler's Second Law, Kepler's Third Law, which basically says that the square of the period of a planet around the sun is equal to the cube of its radius, or the cube of its what they call the semi-major axis, which in a circle is the radius. This equation is from basically a form of Newton's, I don't know which law of Newton it is, but it basically says that the centripetal acceleration is equal to the gravitational acceleration. First thing I want to do is modify this equation so that it has the same variables. Omega is 2 pi times the frequency, which is going to be 2 pi over the period. So that makes this equation, our omega squared becomes 2 pi over p squared. And then we'll just multiply that by r equals g m over r squared. Multiplying by both sides by, let's multiply both sides by r squared p squared. R squared p squared. And I'll go ahead and divide by g right now too. Divided by g. Reason I'm doing that is I want mp squared on one side, like this equation has, and I want my r cubed to be on the other side, like this equation has. That'll clean up the right-hand side, so we'll just be left with the mp squared. The r squared cancels out with the r squared, and the g cancels out with the g. The left-hand side has this new constant in it, 4 pi squared over g. Now this equation is in System International units, so as a matter of fact, I think the thing to do right now is to go ahead and divide out that, and we'll have mp squared over r cubed. Now that is going to let us get a handle on exactly what the units on this side of the equation is. We can do the same thing with the other equation, which was much more simple, and which would just be mp squared over r cubed equals 1. And this one is going to be 1 solar mass times an astronomical unit squared over a per year cubed equals mp squared over r cubed. Sorry, period is in years and r is in astronomical units. So this one is going to be 4 pi squared times over g, and the units here are going to be kilograms meter squared per kilogram. Sorry, kilogram sec. Let me fix this again. This is years. So this is kilogram second squared per meter cubed. So now this becomes a problem that I can actually approach, because it's simply a conversion of a unit to another unit. The mass of the sun is 2 times 10 to the 30th kilograms. The length of a year is 31.5 million seconds, and the 1 astronomical unit is 150 billion meters. And what we're going to be comparing that to is 4 pi squared over g. G is 6.67 times 10 to the negative 11th. And if I recall correctly, that's usually given in Newton meters squared per kilogram. A Newton is a kilogram meter per second squared times meter squared over... Okay, I stand corrected. That it is a Newton meter squared per kilogram squared. Now hopefully, if I've done everything right, these two things should come out to be the same quantity. Plugging both of them into the calculator, I get 588 and 599 billion. 591 billion. That's pretty close. So I know that in concept, I'm doing everything right. But now I would like to create a challenge problem for this. What I just did was I converted it to a kilogram meter second question. What I want to do now is I want to convert it into a Jupiter masses, meters, and days equation. Jupiter's mass is 1.89 times 10 to the 27th kilograms. I'm going to take that divided by about 2 times 10 to the 30th kilograms per sun. But I don't want to put the mass of Jupiter in here. I want to put the mass of the sun in Jupiter masses. So I want the reciprocal of this. So this equation is 1,058 Jupiter masses and 365 days squared. And then this is going to be 150 billion meters. Wikipedia gives the moons of Jupiter's semi-major axis in kilometers. So let's instead of using meters, let's change this to meters. So it'll be 150 times 10 to the 6th kilometers. The change in the distance went down by a factor of 1,000, and the change in the effect goes back down by a factor of 1 billion. Alright, let's see how this works. We've got basically this number is going to be equal to mp squared over r cubed, right? This number here is our period in days, and this number here is our r in kilometers, and the mass in this case is going to be equal to 1 Jupiter mass. So all I want to do is take p squared over r cubed in each case and see if they come out to be 41.7 times 10 to the negative 18th. So to do this quickly, I'm going to run in here to oh boy. Okay, it's doc, file, new document, add data and statistics. No, let's try that again. Doc, file, new document, don't save. And I want to add lists and spreadsheets. I'm going to call one of these R, and the next one I'm going to, wait, is that where I put the name? R? Nope. Oh yeah, it just took it a second to change it to a lowercase. Call this one P. Enter in my radiuses, 421,700, 671,034, 1,070,412, 1,882,709, and then enter in the periods 1.7691, 3.5512, 7.1546, and 16.689, and then I will be entering, this one will be called, well, it's going to be our constant, so I'll just call it constant, and it will be equal to p squared over r cubed. Let's just type that in. P squared over r cubed. And that is a column reference, yes. And that is a column reference, yes. Let's try that again because it didn't work. Equals p squared over r cubed. And we're going to say this is a variable this time. Got to answer correctly both times. Can I just edit that so that it doesn't have that bracket in it? P squared over r. Don't want the bracket in there. Yes, I want to proceed. Variable for that one. And okay, now you can see if the column were wide enough, it would say 41.7 times 10 to the negative 18th in each case, which is to 3 significant digits exactly what I have up there. Okay, I have one more example that I wanted to do that was about angular resolution, and I have an equation here with lambda given in meters and diameter given in meters and theta given in radians. What I'm going to do is solve this equation so that the constant appears on one side and everything else is on the other. So I'll multiply by d over lambda equals 1.220. And this is going to be meters times meters over, meters times radians divided by meters, right? But I want to convert that so that it's 1.220. How many micrometers are in a meter? So I'm going to say 1,000,000, 1e6 micrometers. I'm going to convert radians into second. I want to know how many arc seconds are in a radian. So I'll start with 1 radian. And how many radians are in a degree? We've got pi radians makes 180 degrees. And then we want to get rid of that degree, and replace it with arc seconds. There are 3,600 arc seconds. That's a 0 in 1 degree. I'm just going to continue using this document. That might be a bad idea, but I'm going to go doc, edit, doc, insert a calculator page, and just calculate 1 times 180 divided by pi times 3,600. And we find that 1 radian is 206,000 arc seconds. And then we'll just divide, since we want lambda. Wait a second, diameter is in 1 meter, so I want to use 1 meter here. Be careful with the diameter. And then on the bottom I have a wavelength of 1,000,000 micrometers. Okay. New discovery. You can make this screen smaller by adjusting the bottom of that window. 1.22 times 206,000 divided by 1e6 is 251 times 10 to the negative third. So that gives us an alternative way of expressing this, which is theta equals 0.25 lambda over d, where theta is in arc seconds, lambda is in micrometers, and d is in meters.